Good morning, everyone. Good morning, everyone. Welcome to another episode of Sound Talk Show. We are going to code Wolfram language today and doing plane curves, special plane curves. We are going to recreate this image. This image is done like 30 years ago. So we're going to recreate it. So it's going to be Wolfram language coding, also known as Mathematica. If you are watching offline, play at 1.5 speed because I ramble. If you are watching live, say hi. Love to see your comments. Okay, so Wolfram language, also known as Mathematica. So play at 1.5 speed. Okay, so let's begin. So my keyboard, let me show you. Glove 80, fantastic Glove 80 keyboard. Nulia trackball. Logitech 405 with the best thing 502, G502. The best thing is the spin wheel. Infinite spin, and the ultimate hacking keyboard, and also let me show you this delay and delay. This is Swarboard, the most fantastic advanced ergonomic keyboard device. Okay, so I will get to it eventually. You can watch videos of all these. I have video reviews on YouTube. So this is again SVALBOARD, Swarboard, magnetic switches. So fantastic, okay? I'll be using it sometimes. So let's start to code Wolfram language. Say hi if you are here. Let's stop that. So can you see my screen? Yes, okay. So Wolfram language, Sound Talk Show today. So let's go to Sound Talk Show today. So we're going to code. So Wolfram language, go to xarli.info, my website, and or search for Xar Wolfram language tutorial. You can see where to download. It's free, and I have the complete tutorial for this language, the most advanced programming language by far, better than Haskell, Python, Ruby, Lisp, or Rust. By far. So, but mostly it's used by mathematicians, scientists, engineers. Okay, but you use it just like Python. Okay, it can do artificial intelligence, machine learning, neural networks, like 7,000 functions building. Okay, so Wolfram language tutorial, download it, go read it. And today we're gonna do so here is my plane curve packages. Today we're gonna do okay, let me get on to the. Today we're gonna do the hypocycloid, and hypocycloid. Okay, so let's begin. So hello Dulce. So what we're gonna do? So first of all, let me explain what are these. Okay, am I ready? Let's see. So explain what they are. Okay, so let's do that. Okay, so hypocycloid, and it's easier. It's the best way if you just watch your animation. Okay, so let me show you animation. So you go here. Let's enlarge this window so that close that. So go back here, enlarge the window, and not dev. So this hypocycloid, they are also known as spiragraph. So you can see there's a Wikipedia article about it. I have this toy back in 1980s when I was 10 years old. So it's like great fun. So you generate these curves, and one thing I learned from Wikipedia is that they, why they have these, because one of the reasons is that when they print money, you can see US dollar, they have these kind of curves. So why do they put that there? Because these curves, it is given one of them, because there are millions, infinite variations. So given one of the drawings, it is almost impossible to find exactly what are the parameters to create these drawings. So they print it on the dollar bill, so it prevents counterfeit. Of course, today you have much more technology like hologram or whatever transparency. So anyway, so back then that's one of the reason they created this curve. So basically that's how it works. So you roll a circle around another circle, then you put a point fixed on the rolling circle, then it will trace out a curve. So it will trace out all these varieties depending on the distance, the size of the two circles, or the distance, where is the fixed point on the rolling circle. So the rolling circle can be inside the larger circle, or it can be outside. Do they have an animation of that? They don't have, okay. So anyway, this is known as spiragraph because, some toy company marketed as and trademark spiragraph. Okay, so but their technical name is called hypocycloid, epicycloid. Okay, so there it is. Hypocycloid, epicycloid, that's a blue one. Hypocycloid, that's a red one. Then you have epicycloids. Then you have hypocycloids. So all these are spirograph. That's a technical name for them. The mathematicians, for mathematicians. And there are many special cases. For example, all these are called rows, curves, roses. The most common are these. You can see. Can you see my screen? Am I doing good? Say hi, hello, fellow, blue 3. Blue 3, hello, fellow Python scripters. So you see, these are called rows curves, and these are well known. You learn them when you do calculus, when you take class in calculus, and they are special case of the rolling circles. So I have an animation. So let me show you animation. Okay. So anyway, so all these are special cases. So here is an example. This specific one is called asteroid. Okay, lots of interesting properties, and very interestingly, it has a property such that you can generate the exact same curve in both ways. So rolling a circle inside the circle, that is 1/4 of the radius. So you generate a asteroid. But you can also generate exactly the same curve by rolling a circle that is 3/4 the radius of the larger circle, exact the same curve. And you can have linkages and mechanism that connects these two together, so they trace out the exact same point. Do I have that somewhere? Yeah, so it's lots of mathematics. You can actually see it here. So this is a GeoGebra, using GeoGebra. Let's see if I can magnify. Okay, so using GeoGebra, can you see this? Let's see. Let's magnify that. So let's drag this point so you can see the blue curve inside is the asteroid. And all these lines, you see, all these lines are mechanism, ways to show you how can you actually trace the curve, create the curve. In fact, without rolling any circles. So there are so many properties. You can trace the curve by rolling a circle, or you can trace the curve by all these geometric constructions. You can see, and by the way, the red curve outside of it, that is another asteroid, another cycloid, hypocycloid, and it can. And another property is that it is actually the radial curve, or was it? No, the radial curve, the blue ones. So anyway, so this interactive geometry application is called GeoGebra. Okay, so I have like hundreds of them showing these interesting properties. It's free. It was open source like 15 years ago. Then they became very popular and they made it closed source. So that is extremely nasty. So anyway, so let's see the rose curve. So I'm just gonna talk random a little bit. Okay, so for example, here's a rose curve, and let's see what does this one do. You can, oh yeah, you can animate it. You see, I mean, so this is like rose curve of different parameters. Now let's go back to a easy one. So you can see at some point they become just like that. Okay, so this curve is created by rolling a circle around another circle. Okay, but if you change the circle size and the tracing point, then you got all these variations. You see, so this family of curves is called rose curve. Okay, and they are just a special case of the spiragraph, special case of the, so there are so many infinite varieties of these kind of. So GeoGebra, interesting, you can, try, you can, use it, and you can check out my website and, and get all these interactive applications. It's amazing. So if you are learning math, this is tremendous fun. And this one is particularly very interesting because this, what is this showing is called caustics. That is, you shine a light ray. So in the center, you have this blue curve of three, like shaped like a triangle. It's one of the, it's called deltoid, which is a special case of hypocycloid, meaning you roll a circle inside the larger one. Okay, so you can create this deltoid, this triangle-shaped curve inside. Okay, but then you put a point. Let's see, where is it? Basically, you, for any point, you pick a point on the plane, and you shine light rays towards the curve, and then it reflects off or refract off. Then it will form. You can see it forms this shape. Okay, it forms this diamond shape, and that diamond shape is the asteroid, which is a looks like a diamond, which is a special case of hypocycloid. So again, the diamond shape can also be created by rolling a circle inside another circle. So you see, so the inside you got this triangle shape deltoid, which is a special case of hypocycloid. But on the outside, if you shine a light on the triangle shape and it reflect off, then you got this so-called envelope, this diamond shape, and that is asteroid, which is another hypocycloid. So these amazing and fascinating properties you can see. So I'm moving this point P around. That is the that is the light source. So this demonstrates, doesn't matter where is the light source, their caustics, which means the reflection and refraction, will create the asteroid. Okay, so in other words, the caustics of a deltoid is a asteroid, regardless where is the origin of the light source. So that's what this application demonstrates. Okay, so that's about GeoGebra. So let's go back to so this is asteroid, so remember. So let's look at okay, so let's look at deltoid. So can we see, so asteroid can also generate this way, so amazing properties. So let's look at, so here it shows where the deltoids caustics, which is the light ray refraction, generates the asteroid. So there's a connection between them. And here's a deltoid. Okay, so fascinating. So actually, I don't know what's the proof, so I did this like 30 years ago, starting in 1994. I write programs in Mathematica Wolfram language to generate them, and today I'm just updating them. Fascinating. Okay, so let's go back. So is it interesting? Did God write the universe in Lisp or Wolfram language? Well, Wolfram language is a family. It's a particular case of Lisp. If you don't know yet, let me quickly show that digression. Okay, let me quickly show that the equivalence of Lisp and Wolfram language, if you don't know that yet. So Wolfram language tutorials by videos. So I have lots of hundreds of videos talking about Wolfram language in the past. These are the best ones I collected here. And Wolfram language mod packages. Okay, so these are all packages. Most of them are for plane curves. Like for example, this one specializes in generating animations. Okay, so it's all free on GitHub. So download Wolfram language and get them. And some are for plane for tilings, another fascinating subject. Okay, so these are for trochoid. That's the topic we are talking about today. You can generate all these. And this package is not for, if you want to show the rolling circles, then you want this one. Okay, the animation, you create animation, rolling circles and other animations to generate all sorts of curves. And but if you want, given a curve, you want to change their parameters. For example, the circle size of two rolling circles, a circle rolling around another. But if the circle size are different, they trace out different curves. And you want to show not the circles rolling, but you want to show how the change of circle size create different images. That's this one. That's what this one is for, trochoid plot. Okay, so you can see, and you can also generate an animation of it like that. So you can see you change one of the parameter, they become smaller in different shape to different ones. Fascinating, beautiful. And also this one is interesting because this one shows that a line segment can actually be generated by rolling a circle like that. Okay, so let's go back. So those are Wolfram packages. I'm gonna so download that, and I'm gonna show you how rolling a line, a line segment can be generated as a by rolling circles. Okay, so here's some animations. Let me get back to the Lisp and Wolfram language thing. Okay, so you got this animations. Okay, and where is the single line? Okay, that would be hypotrochoid. You see, this shows a line segment can be actually generated by rolling a circle inside another of half radius of the larger circle. And ellipses can also be generated that way. And here we see the deltoid, we see the asteroid, and we see other fancy ones. Rose, this is rose. Okay, that's about that. So let me show you about how Wolfram language is a Lisp programming language. Okay. So Wolfram language history, there you go. Wolfram language version history, history of notebook user interface. Today it's very popular. You have this Julia, Jupyter notebook. Where does it came from? It came from Wolfram language 40 years ago, starting in 1998. The notebook interface came from Wolfram language. Okay, let's start Wolfram language. So I highly, it's my favorite programming language. It's my first programming language, but it turns out it's also my favorite after all these years. So hold on a second. So Wolfram language, shift enter to start, to launch it, to start the kernel, and magnify. Okay, so that's about notebook interface. Then we want to go Wolfram language history. So Wolfram language is basically based on Lisp and APL. Okay, so here's old documentation like 30 years ago, and APL. Okay, so for detail, Wolfram language versus Lisp, you can see Wolfram language got every, Lisp language. Why is it special? Because you can list about 5 things about Lisp that is different from all other languages. So one of them is everything are symbols. Check. Same thing with Wolfram language. Everything are symbols. Everything is an expression. Check. An expression is either atomic expression such as numbers or string, or a list. Check. Also true in Wolfram language. Purely nested syntax, true. In Lisp you got paren. So you got all these parentheses. So like this is Lisp code. Wolfram language is exactly the same, purely nested syntax, but you use a square bracket instead, and you put the head of the expression outside. So, and predominantly functional programming, check. In both cases. Reader macros, exactly. So Lisp, you got this, square bracket for vector. You got this apostrophe for quote. You got backtick for quote, but evaluate parts of it. You got comma to indicate which part you want to evaluate, and you got the pound sign. These are in Lisp they are called reader macros, and in Wolfram language you have a more elaborate version. So so in Wolfram language actually you can have infix notation, but they are equivalent to the nested version. So here is a complete list of them. Called reader macros in Lisp. But in Wolfram language, they are just called syntactic forms, okay? So you got that. Then you got list macros. So in Lisp, you got list macros. But in Wolfram language, you got like a glorified list macros, which is pattern matching, symbolic pattern matching, or also known as term rewriting system in computer science. So if you take the computer science perspective, it's called term rewriting system. In fact, that's how Wolfram language works, the entire language. So imagine if you are a Lisp coder, Wolfram language is such that every function you write is a list macro. Okay, that's basically all you do. So, okay, that's the Lisp in Wolfram language. Then the other thing is APL. APL programming language is like, so the main thing about APL language is 2 things. They use short Unicode symbols for function names. That's one thing, which is not too important because it just rename functions. But the other thing about APL that's an innovation back then is that they treat every function, every argument as a matrix or array. So this array or nested. So you got matrices or of any dimension. So whenever a function takes an argument, whenever that argument is a list or array or matrix, it automatically applies the function to the whole elements. So it's like map. So in Python, in JavaScript, in Java, we have the map function from basically from APL, okay, map. But the thing about APL is that it does the map automatically. So you don't have to manually say maps a function to something. Whenever the argument is a list, it automatically map, okay? So that is APL. That is the core characteristics, the innovation of APL. APL stands for A programming language. Okay, so that's the case in Wolfram language. Okay, so Wolfram language got the Lisp characteristics, APL characteristics, and every function in APL is in Wolfram language. APL is small, like you got 30 functions, that's it. But then, so besides these two, Wolfram language does mathematics. So, symbolic, solving equations, integrals, derivatives, and so on. So these three parts, the Lisp characteristics, APL, and solve equations or integral and differential equations or vectors or solve matrices, that basically makes up the Wolfram language, what's known as Mathematica. Okay, so then you can see the details. So for every part, like almost like everything about Lisp, in Wolfram language there's a counterpart. Okay, and basically exactly the same thing, except the syntax differ a little bit, but exactly the same concept. So for syntax, for example, for comments, for grouping expressions, for arithmetics, for booleans, then for variables, assignment, flow control, if, else, which, switch, condition, and and loop, while, map, see, do times, and data structure. So in data structure, in Lisp, basically everything is a list. Then you have a hash table, basically. List and hash table. And, well, you have vector. Okay, so in Wolfram language exactly the same. So list and association. So every data structure is just those, mostly just list. Okay. So for example, Wolfram language does not have hash table until about 10 years ago. For the first 20 years ago, for the first 20 or so years of Wolfram language, there's no hash table. Everything is just a list. So what if you want a hash table or dictionary? Well, you just have a list of pairs, just like Lisp, called association list. So and so you can check out that. Okay, so let's go back to so is that interesting? Keep your comments coming. Okay, so let's go back to start to code some Wolfram language on the mathematics on the on these things. Says, you have influenced me to look into more. I didn't know it was a Lisp. Why is Wolfram not used more often in some of the places Lisp uses? It's simple. The answer is simple. Wolfram language is not free. In fact, if you want to buy it, it's like if you want to use in a corporation, like professional organization, it's like $2,000, $1,000 back in 1990s. They have student version, which is $250. So it's a very commercial entity. Okay. And most coders, they don't like it. Like the C and Unix people, they don't want things that's not free. They want free. So then the open source became very popular since year 2000. Everyone demand open source. So then basically that killed all the commercial compilers, and so everything is like open source and free. But Wolfram language remained commercial. So today you can download the you can download it free starting about about 5 years ago. Okay, so you can download it free but it's still commercial. It's not open source. Okay, the free version provide everything. It's not a crippled, so it's like exactly the same as if you buy, if you pay it. If you pay it, there's a student version, there's a hobbyist version, like $300, something like that. Okay, check their website. So yeah, it's commercial. I mean, yeah, so the open source, people want free things, but now you got the free version. Okay, so that's about Wolfram language. So hello, Hank. Okay, let's start to code. Okay, so close that show. So let's start to code. I want to code, what are we coding? So Epicycloid. So I want to regenerate this graph. Let's try that today, okay? So open that. So go to the top.mb. You can see there's a Wolfram language notebook. These are 30 years old. So open it, make a backup, open it. Okay, so let's move it here. And you can see it says, Asian notebook. Do you want to update the appearance? Yes. Okay. Then magnify. Okay, so these are my old, like this is 1995. Many of these are obsolete, but I have an updated version on my website and on GitHub. So description, okay, so how are we gonna do this? So you can see this is ancient. Okay, so this is the graph we want to recreate, okay? Now this is 30 years old, now remember, so okay, so we need to do that. Okay, so let's start with something simple. Okay, so let's put here, let's save it. Untitled spiragraph. Okay, so it's calling paraplot and calling that is my my packages. Okay, so let's see. So you can get those. Okay, let me start to do this. So what do you need? So this package is so this one is for plain curve formulas. Okay, so yeah, so let's focus on getting this done. So okay, so go to curve formulas. Let me just get it. Okay, so we are doing, what is this one? This one is hypocycloid. Okay, so this one is hypocycloid. Okay, let me just grab the formula. Okay, so hold on a second. So go to talk show. Go to today's talk show and start a coding block from language. Okay, paste the code there, and okay, then search hypocycloid, search. Okay, where's the definition? So the definition is here. That is the formula. Okay, copy that, close that. Okay, now show in browser. So there's a Wolfram language. Let's pop it out, paste it here. So this is the formula. So we want to so let's copy this. Okay, so we need to make this code work. This code right now won't work because it's calling a package. I can load the package, but I don't want to do that. I want to show you how to do this without, without like special package. Okay, so you define this function hypocycloid, and which has 3 parameters there. Let's show. Okay, 3 parameters. So hypocycloid is a special case of hypotricycloid. So it becomes so it becomes 1 and 1 over n, 1 over n. And what is hypotricycloid, which is this one, and it is a function of t. So here's the formula: a and b. A and b are the radius of the circles. So circle A, circle B, radius h is the distance from the center of the rolling circle. That's the tracing point. Okay, so anyway, that's the formula. So then you want to okay, so let me just quickly show you something. Okay, so parametric plot takes 2 functions. One is the okay, so let's not do that. So parametric plot takes 2 arguments. One is a function. The second part is a parameter t from 0 to, let's say, 30. Let's say 10 pi. Okay. So you need to define a and b. Okay, clear. A, b. Okay. Then you assign a equals to 5, a equals to 1, b equals to, let's say, 1 over 3. Okay, so we can now plot this. Okay, no go. Okay, something is wrong. So why is it wrong? Because h is not defined. Yeah, so we need to define h. A, B, h. Okay, so h is 1.1 over 3. Okay, copy that. Now, if you are wondering what is h, let me, there it is. Okay. Okay, so what is h? H is the so let me show you an animation. Do we have an animation? Yeah, you see this bar extending far out from the yellow circles. So the distance from the length, so h is the length of that bar. Okay. So if the length is different, you have different curves. So here the formula a and b, a is the larger circle radius, b is the radius of the smaller circle, and h is that length of that bar. Okay, so you got that. Okay, so and what's the other thing? So if you change it to 3 over 7, so if you change this to 3 over 7, then you get that 7 star thing. 3 over 7, shift enter. Fantastic. Okay, so you don't need any packages. You can just, in fact, you can go to Wolfram research. Like you can go to the Wolfram Alpha, and it will. I'm pretty sure. Okay, so Wolfram Alpha website. They have somewhere that allows you to evaluate Wolfram language code online. Like, okay, so let's see. Okay, I missed some part of it. So let's copy again. Turn on JavaScript. Yes. Wolfram Alpha doesn't understand your query. Okay, so yeah. you need to go to somewhere. Wait, try the following. Okay, Wolfram, oh, wow, it typeset the thing. Fantastic. So in Wolfram language, you can typeset the thing just by pressing Ctrl-Shift-N. Okay, it's beautiful. That's the beauty of Wolfram language. You don't have to learn LaTeX or tech complicated. Just Ctrl-Shift-N will do it. Okay, so we got that. So let's move on. So okay, God. So now we need to work on this code. Yeah. Okay, so this code will generate these graphics. Okay, so this is 30 years old graphics. So let's make a breakpoint there. So we need to get this code to work. Okay. So I'm doing this, this particular graphics is to show, let me go back here. Okay, so this particular graphic is to show, it lets you get a general idea of what the parameters, what the curves look like for a certain parameter, because there are so many of them, so I've chosen, this is carefully chosen values. So it is intended to show you that, so at a glance you can know what kind of parameters will generate what kind of curve. Okay. So for example, if you see these 6 curves, you can see the number 6 there. You see -1/6 or -5/6. So for these 5 curves, you can see the number 5, -1/5 or -4/5. For this one is 4, for this one is 7. Okay, so and this one is 4. So you can like get a sense of what it looks like. Okay, so let's try to update this. Okay, so let's see. Oh my God, this is kind of advanced code I wrote like 20 years ago, 30 years ago. The okay, parametric plots, hypocycloid. Okay, so I need to define that. It's epicycloid. Okay, I got hypocycloid, but I don't have epicycloid. Epicycloid is basically just a change of sign. So get let's see, curve formulas. So what we need the epicycloid formula. Search for it. There it is. Copy back here. So let's put it there. Okay, so this part we remove. And where is the formula? Okay, so search for the formula. There it is. Okay, copy, close, and paste it here. And this is the inline documentation. Okay, move it up. Okay, so we got hypocycloid, epicycloid. So hypocycloid is defined in terms of hypocycloid. Epicycloid is defined in terms of epicycloid. Okay. Okay, so we need some kind of clear, because that makes it so that you can, so when you reevaluate, they will clear out all the rules and stuff. Hypocycloid. Okay, so that then you need the epicycloid. Okay, yeah, so clear them. then inline documentation, then the actual definition here. Okay, then you, okay, so okay, so you got this. Okay, you got this. Actually, it will just work. All you have to do, it will just work, I'm pretty sure. So go back here, select all. Wait a minute, shift enter. Let me make a screenshot of this. Okay, select all, paste. No, not that. Copy all, select all, paste. Okay, so we got a code here. Now shift control N to make it typeset. Okay, so now we can evaluate it, and hopefully it will create this after 30 years. Okay, let's see. Yeah, shift enter. Okay, do it. Okay, no, wrong. Yeah, graphics array is obsolete. Okay, so yeah, so it's obsolete. You need to use graphics grid, but however, it still works. Now, you see, you need to change the thickness. Yeah, I kind of like this new thickness, new default thickness. Okay, so it works. This minor detail graphics array is obsolete. You need to use graphics grid, which is trivial to change. It doesn't matter much. Okay, so graphics array is a function that just takes a list of graphics. Then they will try to arrange them in a like grid. So that, you know, so they replace with a new function, graphics grid. So anyway, so that's it. We did what we wanted. Fantastic. So let me copy this. So cut graphics. Let's see. Export. Copy graphics. Save graphics as. I don't want PDF. I want JPEG. So you got PDF, HTML, BMP, JPEG, PNG. That's what we want. Okay. Then this Windows interface, XX. Okay. Now go to desktop. Refresh. There is a graphics now opening in the dedicated graphics. Fantastic. Okay, so copy the file path, close it, show metadata. Okay, there's a lot of metadata. We make a backup. Now remove metadata. Okay, show metadata again. Now it's metadata is removed. Okay, now copy the file path, close, go to XR Talk Show, today's talk show, show in browser, go to the Hypocycloid page, open it there, and search for PNG. So this is the old image. Now let's put a new image here. Link file, show. There it is. Fantastic. This is update after 30 years. Yeah, it's much better. And then move the image to the current directory. Wait. Move it to the current directory. Let's just say there. And rename it. Okay, this is my old naming convention. Let's make it Epicycloid, Hypocycloid, gallery. Okay, let's just say. Okay, redo the figure tag. There you have it. Okay, that's it for today. Fantastic. I hope you like it. Anything else? I think, yeah, that's it for today. I need to code, so I need to code a lot more. I need to you see this package, I need to, and there's a lot of animations and stuff I need to redo. Okay, bye guys. I think that's it. So this old image, let's see, this is 36 kilobytes. Okay, let's look at the new image, 566. Okay, you need to optimize it. Make a backup first, optimize. Okay, refresh. Now it's 242 kilobytes, so it's like, yeah. If you like my stuff, okay, support me. Go to my xali.info, pay me, okay. Go to xali.info. You can, then xali.info, then all the way down, Patreon me, Amazon gift card, PayPal. I prefer those, okay. Send me $100. Or you can get my entire website of all the programming tutorials. It's about 6,000 pages, 3 gigabytes of information written in the past 30 years. You can pay me $300 PayPal or Amazon gift card, and I'll send you a zip version, okay? Or you can buy my Emacs tutorial and JavaScript tutorial. You go there. If you are interested, you'll find the the link to pay me and get the zip file. Thank you guys for watching, and bye guys. Like it very much. Thank you. First time I see Wolfram in action. Fantastic. Hey 10. Bye. Okay, so close down.